Hi everyone, welcome to Ignite classes. Today we are discussing the working of moving coil galvanometer. Moving coil galvanometer. So let's start. First we are going through its structure. In between two magnetic poles, north and south of this shape, we are placing a circular conductor. This is the top view of the system, and there is a string attached to this at the center of this circular current carrying conductor. Circular conductor, and we know that the field lines are acting, magnetic field lines, radial field lines are acting on this circular conductor, and when we pass current through this conductor, it will experience a torque, a magnetic torque it will experience. Okay, so we know that at the center there is a spring, small s, and when we apply this current to it, due to magnetic torque, it will start to rotate. At the same time, the spring will exert a restoring torque, so that this magnetic motion due to this magnetic torque is balanced. Okay, so magnetic torque, we know the equation to find the magnetic torque, that is m cross b. Okay, where m is the dipole moment and m that is equal to I, the current, into area of the loop. Okay, here area is pi r square, then area of the loop, so I into a. And for n turns, here in this case, this in this circular current carrying conductor, it is winded with n turns of a wire. Okay, so it is this magnetic moment, it become nia, then into b sine 90 in this case, as the magnetic field lines are acting perpendicular. So sine 90 it is equal to 1. So restoring torque, that is magnetic torque, it is niab, and this is balanced by the restoring torque. Torque restoring, that is equal to k phi, where k is the torsional constant, or we call it is the distortion per unit twist. Torsional constant is the k, and we call it, its other name is distortion per unit twist. Distortion per unit twist. So this restoring torque, that is equal to k phi, and we know that the purpose of this restoring torque, it is to balance the magnetic torque. So magnetic torque equal to restoring torque. Okay, so that is niab is the magnetic torque, niab, that is equal to k phi, is it? Then we are finding phi by I, because this is the current sensitivity of the galvanometer, that is equal to NAB by K. Okay, this is the equation to find the current sensitivity. Then we know that the galvanometer, we use galvanometer. This is, I am drawing a galvanometer. It contains scales, and there will be a needle. And if there is no current, the needle will stand in this way. And if current is flowing in this direction in a circuit, then this needle deflects to this side. Okay, if current is flowing in the opposite direction, this needle within the galvanometer deflects in this direction. Okay, so galvanometer, we use it to detect the presence of current in the circuit. Okay, galvanometer as such, we can't use galvanometer as such as ammeter. We have to convert a galvanometer into ammeter. So how we can convert this a galvanometer into ammeter? By modifying its structure, or modifying the parameters behind its working. So we have to discuss that. So how a galvanometer can be modified into an ammeter? So I'm drawing a galvanometer, and this Rg, it is the resistance inherent to this galvanometer. I am drawing it as Rg. Then just connect a resistance called, we call it shunt resistance, having very small resistance compared to that of Rg, galvanometer resistance. Then if current enters the circuit, this it will, most of the current pass through this, and only very small portion of the current pass to this Rc. Okay, then by connecting a small resistance, shunt resistance parallel to this galvanometer resistance, then we get what? Ammeter. Okay, this is how we can convert a galvanometer into ammeter. So here we have Rg as well as Rs, so they are in parallel. Rg is the, and Rs is the, and so, and we know that Rg, it is very greater than Rs. So effective resistance, it become Rg into Rs by Rg plus Rs, since they are parallel. But we know that Rg, it is very greater than Rs, so we can neglect this Rs at the denominator with addition. So what we get? We get Rs. So the effective resistance, that is equal to shunt resistance. Okay, then so why we are converting this galvanometer to ammeter? For what we are using this ammeter? We use ammeter to measure the current. To measure the current, we use ammeter. But this galvanometer we use to detect the presence of current, and even current in the micro range, microampere, will give current in microampere will give full scale galvanometer deflection. So that's why we have to convert galvanometer into ammeter to measure current. Okay, then how can we convert a galvanometer into voltmeter? That another topic that we have to discuss. Okay, so just connect, this is galvanometer, and this is galvanometer resistance, and in order to convert this into voltmeter, just connect a resistance in series. Okay, in series with this galvanometer resistance, and the value of this R, it is very greater than the galvanometer resistance. So here we have R plus Rg, it is equal to, approximately equal to, we can neglect this Rg, since capital R, it is very greater than Rg. So effective resistance of this voltmeter, that is equal to R. So that is this galvanometer, and this is Rg, and when we connect a shunt resistance in parallel to it, this is equal to what? This is equal to an ammeter. Okay, then, and this galvanometer, and this is Rg, and when we connect a large resistance in series with it, then it is what? Then it is equal to a voltmeter. Okay, yes. So today we have discussed what is moving coil galvanometer and its working, and we know that this NIAB, that is the magnetic torque, that is equal to K phi for a moving coil galvanometer, such that the current sensitivity phi by I equal to NAB by K. Okay, but we have to find the voltage sensitivity as well. So current sensitivity phi by I, that is equal to NAB by K. So I can NAB by K. So I can take this what I into this side. So NAB by K into I. Okay. Then we are finding voltage sensitivity, that is phi by V. So just divide both sides with V. So phi by V, that is the voltage sensitivity, that is equal to NAB by K into 1 by R, where we know that according to Ohm's law V equal to IR. So 1 by R equal to I by V, we know. Okay, so this is the voltage sensitivity. That's all. So if you like the class, please subscribe the channel to watch all the classes we are uploading, and if you like the class, don't forget to press the like button also. Okay, thank you.